Hey you guys, this is Mr. Sal. So we just had the parent-teacher conferences, but I'm not feeling very well, probably from the conference. So I'm not in class today. Sorry about that, but I'm still making this video for you guys. So if you need to, you can watch it at home on YouTube. But yeah, again, sorry I can't be in class. But behave yourselves for the sub. Sub's doing their best. Thank you, Sub, for teaching the class. If anyone misbehave, please tell me. Write their name on a piece of paper. I will find it when I get back, and I will take care of them. But thanks for taking the class. In the meantime, you guys take a moment and find the slope for both of these tables. Now these ones will work pretty much the same way. There'll be some pausing in between so you guys can try these out. And then we'll do some explaining. You should try them out though so that you can learn when we do some explaining, figure out what you need to fix, figure out what you know and what you don't know, and then find out how to know what you don't know. But yeah, I do expect some pausing between some of the problems. All right, hopefully you got these answers. All right, so looking at these, again, we can choose any 2 points on these that we want. But this first table, for example, from -9 to -27, it went down 18. And that is our y value, which is the numerator. And then the x, this one went up by 6. So -18 divided by +6 is -3. That's what we got right here. Well, what about that next one? How do we get -9 out of this thing? Let's choose the 2 middle ones just for the sake of randomness. From -5 to -14, you'd have to go down 9. And from 1 to 2, you'd go up 1. So the sloppage there becomes a -9 over 1, which simplifies to -9. All right, there's the homework. Again, you guys are going to have to score this one just like the last one. I'll put the scores up here. Well, they're actually up 1 point per problem. So just subtract whatever you got from 10. And then we'll take the scores when I get back next week on Tuesday. All right, hopefully you guys got that corrected. There wasn't too many problems. Again, I'll take the scores when I get back. So this is a really good time to pass out the notes for the day. Again, thank you for taking the class. You guys behave yourselves when I get back. I'm not feeling well, so if I get back and find out you guys misbehaved, I will be mad. Do not make me mad, because I'm sick, all right? So be nice. All right, this is on the first page there. What about linear relationships that are not proportional? Are you going to, we're going to further investigate this stuff. Very similar to the way we did the last one. A geometric transformation can relate a linear proportional relationship to a linear non-proportional relationship. In previous sections, we used the geometric transformation called a dilation, which is just making something bigger or smaller. Another type of transformation is called a translation, shifting a line or moving all the points on the line the same distance and direction as a transformation. Well, that is called a translation. For example, if you transform the line y equals 1/2 x upwards by 3 units, every ordered pair that lies on that line gets moved up 3 units. Algebraically, that means you add 3 to every y value, right? So if something was on the line for y equals 1/2 x, maybe it would have been something like 2, 1. Well, the transformation is moving this up 3, which means my y value is going to have to add 3, which changes this now to 2, 4. See that? That's what this is saying. It's very abstract, very algebraic, but it is something you need to understand. To confirm this, the investigation will show us. So let's look at y equals 1/2 x. We'll make a table of values. So I have some values here. 0 is an important one because it kind of shows us where the y-intercept is. And we'll talk more about y-intercepts later, but I also have other values which are even. There's a purpose for that because in this equation, if we have odd values, it's going to come out as a fraction, which we don't really want. We can have it, but we don't really want it. So this first one, for example, this is our equation. Y equals 1/2 x, but up in here I'm saying that x is, well, Negative 2, right? So negative 2 times a 1/2 would be negative 1. So that's my y value. When x is negative 2, y is negative 1. And we could graph that as an ordered pair. Well, what about when x is 0, right account? Well, the only thing that changes is that y now is 0. Showing that it passes through the origin, and since this has a constant rate of change, it is a proportional relationship. And then the next value, y value, is, x rather, is 2. So my y will become 1. And I can put that in the table. Finally, when x is 4, we find that the y is 2, and I can put that in the table as well. So there are the values. We use the same ones the book did. Very wise to use those even values of x so that the y's come out as integer values. All right, now it asks us to graph this thing, so let's go ahead and graph the points right account. We got an x that's negative 2, y is negative 1, 0, 0, 2, 1, and then a 4, 2. And of course we can draw a line through these points. Bam, something like these. Now, of course, we're going to add 3 to that, and it was shown in the table that you have on your paper. So for each of these y values, I'm just going to add 3. So, for example, negative 1 plus 3, bam, it gives us is 2. Make that a little bit smaller. And 0 plus 3, that's going to equal 3. 1 plus 3 is the 4. 2 plus 3 is 5. Now, these are all y values that correspond to these respective x values over here. Now, if we went ahead and graphed those, let's look at the first one again. Something like these. Now, let's graph these points. So the first pair, right, negative 2, 2. Right about here. The next pair, 0, 3. Next one, 2, 4. And the next one, 4, 5. Right here. Well, I can connect these as well with the line. Bam, there it is. And yes, it was showing right here the whole time. Well, what do you notice about this? All we did is we took this red line right here. Whoops. And we moved it up right here. See that right there? And if we wanted to, we could move it up 3 more, so that would be y plus 6, and then maybe y plus 9er. But it's not, so we're just going to look at it like this, right? There we go. So let's write an equation for this. So notice what we had originally was this y equals 1/2 x. That's important. But then what did we do? Well, we took that line and we moved it up 3. So we would just add 3 to this. Okay? Because each y value was 1/2 of the x, but then we added 3 onto it afterwards. Well, what does this mean? Well, if we look here at the green line, which is represented by this equation, what does this 3 mean? The 3 is the value of y when x is 0, which is shown in this ordered pair. Well, it's shown right here on the graph. That is the line where the green line, passes through the y-axis. That is called a y-intercept. So we have a sloppage and a y-intercept. Okay? Y-intercept is the value of the y when the line crosses the y-axis. Additionally, for all y y-intercept, the value of x will be 0 as it is here. Alright, this is one of those things you guys are going to have to memorize there in the box. The general form of a linear equation is y equals mx plus b. There's a poster for it in the room. Can anyone find it? Of course you can't because no one looked. It's right above the TV. Bam. Found it, where m is the sloppage or rate of change and b is the initial value or y-intercept. As also seen in the example above, the equation y equals 1/2 x plus 3 represents the linear relationship where the sloppage is 1/2, and 3 is the y-intercept or initial value. We did talk about that. Use the information on the previous page to compare and contrast the two relations using a Venn diagram. Be sure to list similarities and differences about their graphs and equations. Bam, I did it. I found it. All of the differences and the similarities, which of course is where it is for the similarities in the Venn diagram. So how is this general form y equals mx plus b for a linear equation derived? Let's start with an example. Graph a line on the coordinate plane to the right that shows through the point 0, 4 and has a sloppage of 2, 3. Label the rise and run on your graph with the right triangle. Redraw and label this triangle in the space provided below the graph. Alright, so that's what you guys are going to do. Let's see, 0, 4, I mean, we didn't have any grid on this thing, so we got to kind of guess on this. 0, 4, about right account. There we go, and it has a sloppage of rise of 2 and a run of 3, so it should go about through this point right account. And maybe this is our line. Well, we can draw that triangle as we did in the previous lesson, right? I've got an up 2 and to the right 3. So over here, I can draw my triangle. That looks pretty good. Up 2 to the right 3. So now what I'm going to do is choose an arbitrary point right here, which is xy again. So this is a y, and this right here is x. Again, we don't know where that point is, but in order to make this triangle right here, okay, we have an x and then a y, but y can consist of this whole value from 0 to y. But this point right here, right, this is 4, so this right here would be y minus 4. So the length of this part of the triangle is y minus 4. Bam, and we got a triangle right here. Based on what we learned last time, these two triangles should be proportional. So in other words, we should be able to write equivalent fractions on this thing. And the first triangle, we got a y minus 4 compared to the x. And then the second triangle, we got a 2 over 3. Well, what would we do to solve this one right here? Well, we'd multiply both sides by x first. So now I got a y minus 4 equals 2/3 x. And then what would I do to solve it? I would add 4 to both sides. Like at these, that becomes a zero pair. And I get y equals 2/3 x plus 4. That's what we wanted to find in the first place. Now let's look at the general case for y equals mx plus b, and we'll graph a line on the coordinate plane to the right that goes through any point on the y-axis called the y-intercept b. And as a sloppage of m, we'll label the rise and run on the graph with a right triangle and redraw and label this triangle in the space provided below. Then, as you can see from the rest of the instructions, we'll find an arbitrary point, x, y. Then we'll create a proportion, we'll solve the proportion, and we should get this y equals mx plus b stuff. So this process should look pretty familiar. Here's what we're going to do. We're going to graph any point on the y-axis, and we're going to call that value b. So as an ordered pair, it would be 0, b, like this. And then it's going to have a sloppage of up m, right? So this is up m. And then to the right one, like this. So give us a point right here. And we got this line going through these 2 points. So what I have then is a right triangle like these with a rise of m and a run of 1. And again, we can compare that to a similar triangle if we choose some point on the line as well. And this would be an x value. And this right here would be some kind of y value. But since we're looking at making a triangle like this one right here, the distance from these 2 points is a y, and then up to this point is b. So this one has a rise of y plus b, and then the run, which we can see right here, or right here, doesn't matter, we can make that a right triangle, is x. So we can make a proportion out of this with equivalent fractions because the 2 triangles are similar, and the green one had a rise of m and a run of 1. So now in order to solve this thing, all I'm going to need to do is multiply both sides by x first. And what happens when we do that is that these 2 x's will cancel. So now I have x times m equals y minus b, and of course we can make that mx. So to solve this now we would add b to both sides, like these. And now we got y equals, well, we could make that mx plus b. Well, that's exactly what we were looking for, it just looks a little bit different. It doesn't matter if we make that y equals mx plus b like this, and that is the equation.